Okay, guys. Today we are going to discuss about intersatellite range rate. What is the story? The story is that if this is the Earth's surface, two satellites, or they call it twin satellites, following each other in the same orbit, like that, and at the same time they are positioned by GNSS satellites, like this, and the distance between the satellites are measured precisely. Let me consider this satellite 1, satellite 2, or it doesn't matter which one. This is the distance between them. Then I show it by row bar. So the question is how this distance is connected to gravity field. So that's the main question. This distance is not constant, and it changes as the mass, there's a satellite rotates around the Earth. They will experience different mass distribution around over the Earth. For example, let's consider that we have a mass here. I will draw three figures. We have a mass here under the Earth, and two satellites are following each other here. When before the satellite moving in that direction, this source, this mass, is closer to the first satellite. This causes that this satellite goes a little bit further, or go a little bit far from this, because it is closer to this one. And when the satellites comes here in this situation, so this mass attracts the satellites in that direction, push them, and this one is pulled. So this distance will be smaller. So, and when the satellites can come to that situation, that the other side is get far from the mass, therefore is far, and this one is far, then this distance increases. So you see that the mass inside the Earth, or mass heterogeneities of the Earth, can affect the distance between the satellites. So if we can measure the changes of this distance for the intersatellite range, or we call it intersatellite range rate, we can determine the gravitational changes inside the Earth. So the question is how? So the first thing that you have to consider is that the energy, the kinetic energy between satellites is, I write it like that: the average velocity of satellite plus the average plus the changes, the line track changes. Oh, sorry, it should be the line track changes. I will explain them later. What are them? Plus radial track change plus cross track change. So what is it? Long track cross. If we have a satellite moving along the orbit, the satellite moves in that direction along the orbit. It's called a long track. A long track. And this is towards or outwards towards the Earth center is called radial track. And here I show it by U bar. And cross track is the one perpendicular to the orbital ellipse. Then we show it with W. So along track is V bar. Cross track is W bar, and radial track is U bar. So if I have this speed of this direction, this movement, we can observe that the highest speed is along the satellite movement or satellite trajectory along the orbit, the highest speed. And these small changes here that you see, the small speed, are too small. So this is the kinetic energy. Let me write it here, is kinetic energy. Let me expand this kinetic energy a little bit more. Then I will write V star. V0 is a mean orbit, mean velocity of satellite, mean along track actually, square plus 2 mean velocity change plus V to U and W. And it is proven that this term is almost zero, not significant. If we consider that, therefore the kinetic energy with this satellite, just this term will be this term, the first two terms. Let me write the kinetic energy by K. Therefore, I can write 1 over 2 average velocity of satellite with the power 2 plus V0 V bar. 2 by 2 is simplified. This kinetic energy can be connected to the potential energy by this equation. If you remember, kinetic energy plus the potential is constant, and it is equal to Gm over 2a. So based on this, we can simply write that. Okay. So this is for, we can simply write two kinetic energies for two satellites, like that. So for the first satellite, I will write K1, which is 1 over 0 square, average velocity, and plus 2, not 2, the average velocity of the first satellite is constant. Is a constant, doesn't matter what it is. And 2, it will be again, plus the potential. Plus the potential at this first satellite is constant, Again, is 0. So not the kinetic energy. Let me write it better. 4 satellite 1 satellite 2. So the same v2 speed plus the potential is constant. Now I subtract these two. I will write, okay, the second equation, or satellite 2, this one, I will write 2 minus 1. Then this term is constant. This one is also constant. Then I can write is v2 minus v equals to, there's a minus here I can put, so I can have v2 minus v1. What does it say? This say that the potential difference between the satellite, the potential that the satellites 2 experience or sense, minus the potential that the satellite 1 experience, is equal to minus of the average velocity multiplied by the difference between their aligned track velocity. That is interesting conclusion. So I can write this potential. I can measure this velocity changes between the satellites, and I have the potential here. So potential can be written in terms of spherical harmonic. For example, for the second satellite at the position R2, theta 2, or lambda 2, I can write, let me rewrite everything. For the second satellite, I have R2, theta 2, and lambda 2. I can write the spherical harmonic expansion in 2 top to infinity, R over R2, n plus 1, summation m minus n minus n. This is v n m y n m, but this side theta 2 lambda 2 at the second, and v1 is the same, but at the position of the first satellite. I write it fast. V n m is 1 y n m theta 1 and lambda. So if I subtract v2 minus v1, simply I come to this 2 sigma, and as you see, VNM is constant in both cases because the gravity field is the same for both satellites. So I can simply write a formula like that. R over R2 n plus 1 minus R over R1 n plus 1 summation m minus n VNM YNM theta 2 lambda 1 minus YNM theta 1 lambda 1. So that's all. And the whole equation, the whole should be equal to minus velocity of the mean velocity of the satellite, line track velocity minus at satellite 2 and line track velocity of satellite 1. So this means that if we can determine this aligned track velocity, we can come to a spherical harmonic coefficient. So we have a system of equations or observation equation having this velocity difference of the satellite and the spherical harmonic coefficients. That's all. But this velocity difference of the satellites, so that's the question is here. These are the velocity difference, not the range rate. Not the range rate. Then what can we do to get the range rate? So it was this is a simple derivation. We have it satellites. For example, satellite 2 is here, satellite 1 is here, and I have this center of the Earth, and this is the long distance between the satellites, which is measured, and this is a long track for satellite 1, and this is the long track component for satellite 2. Is velocity below the beside velocity, and this one is velocity. If I divide these two with side, this angle between two satellites, the spherical geocentric angle. This one will be side 2, and if I continue this one is also side 2. This angle. If I continue that one, and it's multiplied, there's perpendicular to that one I draw. So it is side 2. And if I do this one, and this continue this one, this will be side 2 as well. So this upward is the radial velocity of the satellite 1, and this one is the radial velocity of satellite 2. So the velocity of these changes, or velocity of it will be, I will write it like this, will be the radial velocity of the first satellite, radial velocity of the second satellite, multiplied by sine of side 2, plus velocity of a long track minus velocity 2 of a long track cosine sine. So as you see, the sign of this side is for you is plus here, because they are both pointing upward, and here this one is upward, the other one is downward. So it is probably because of that. And since this distance is around 300 kilometers and is small comparing to the radius of the Earth, or as we already explained, these radial velocities are not that big as they are. Therefore, this term is approximately 0. Therefore, I can write that, okay, and if its psi is 0, this term will be 1. Therefore, I can write that the range rate between the low orbiter, two low Earth orbiter, will be minus a long track. So what does that mean? So we come back to the spherical harmonic expansion that we wrote. What was that? It was, okay, summation for n is 2 to infinity, r second satellite minus r first satellite multiplied by m from n up to n, v and m. Let me clean this part. Y and m theta 2 lambda 2 minus y and m theta 1 lambda 1 equals to, it was, if you remember, 0, and instead of this one we already have the minus, we put rho bar. So that's all. I have an observation equation, and V and M are the unknown parameters, unknown, and this one is the measured. The average velocity of the satellite, we know it, we can compute it. So, and the range rates between these twin satellites are measured by precisely, are measured precisely. Therefore, you can write for each measurement between two satellites, you can write an equation, an observation equation. And how many of this type of measurements you have? You have millions of this type of measurement around the Earth. And when you have a full coverage all over the Earth, you can determine spherical harmonic coefficients of the gravity. This type of it is called Grace type. This is the method which is used in Grace mission